Hello student, my name is Nimesh Prabhakar. I am Assistant Professor at LJ Institute of Engineering and Technology in Instrumentation and Control Department. Welcome to Process Control lecture series. In this lecture, we study about what is first order system. So, first of all, question occur in mind, what is first order system? So, a first order system is one whose output is described by the solution of first order differential equation. That means one system whose output y of t is described by solution of first order differential equation. Mathematically, we can represent first order system or system as a1 dy by dt plus a0y is equals to b f of t. Here f of t is represent input, or it is also known as forcing function. Here a1, a0 and b is the constant and y is represent output. So this is a general form of first order system. Now if we consider in this equation a0 is not equals to 0, that means a0 is not equals to 0, so we can write this equation as a1 by a0 is equals to dy by dt plus y is equals to b by a0 into f of t. Here simply we divide all the equation, and that means left hand side and right hand side by the a0. So we can write this equation as tau p dy by dt is equals to kp f of t into kp. Here tau p we can known as time constant, and this represent the value of a1 by a0, and kp, this is kp is also known as steady state gain or static gain or process gain, and this represent the value of b by a0. Now this is a general equation of first order system. Now we take the Laplace of this equation. So we can write this equation as tau p, and we know the Laplace of differential equation. So we can write simply as y of s. Here y of 0 is the 0. So simply we write s into y of s. Now y Laplace is y of s, kp is constant, and f of t is equals to f of s. Now we take y of s constant in the left hand side. So we can write this equation as y of s bracket tau p into s plus 1. Right hand side term is same as kp into f of s. Now we can rearrange this equation as y of s upon f of s is equals to kp upon tau p s plus 1. So we can write transfer function of first order process as, so this is nothing but y of s upon f of s is nothing but g of s, and g of s is the transfer function. So y of s upon f of s is equals to kp into tau p into s plus 1. So this equation represents the first order system. Now a first order process with a transfer function given in equation number 3, also known as first order leg, linear leg or exponentially transferred leg. Now here we consider in this equation same the second one case we consider if a0 is equals to 0. If first one case we consider a0 is not equals to 0. Now we consider if a0 is equals to 0. That means what? This term is 0. So we can write this equation as dy by dt same as b, this a is gone this side. So b by a1 into f of t. Now we can represent this equation as dy by dt is equals to kp dash into f of t, where kp dash is represent nothing but b by a1. Now we take Laplace of this equation. So we can write this equation as y of s is equals to kp dash into f of s. Okay. Now we rearrange this equation. So we get y of s upon f of s is equals to kp dash upon s. So we get transfer function as y of s upon f of s is equals to kp dash into s, and this case is known as pure capacitive or pure integral system. So this represents the pure capacitive first order system. So this is a first order system. What is first order system? Now next one, we take one example of first order system for better understanding. So we take one example of simple liquid tank or water tank example. Here in the figure we represent one tank. In this system, A is the uniform cross section area of tank, that means area of this tank. Now R, this R is represent flow resistance, that means this output flow resistance is R. Now V is represent the volume of total tank. So we can also write this volume in terms of area into height as A into H. Next one is rho. Rho is the density of material. Here material is water. So rho represents the density of water. Next one is Q0. Q0 or Q0. Q0 is represent outlet flow rate. That means water outlet flow rate. Next one is Q. This Q represent inlet flow rate. And H is the height of water level in tank. That means H represent the height of water in tank. Now from this figure we can write the relation between Q0, that means output flow rate, and resistance R as Q0 is equals to H by R. This represents the linear relation between the Q0 and H. In next lecture we will discuss about non-linear system. Here we discuss about linear system. What is linear system? What is non-linear system? We will discuss in next lecture. So here Q0 is directly proportional to the H. That means in the variation in Q0 and H is directly proportional. That means if flow rate is more, then height is decreased more. This is a linear relationship. And Q0 and R is inversely proportional. That means if resistance of flow, output flow is more, so at that time output flow rate is low, and if flow rate is more, then resistance value is more. So this is a relationship between Q0 and H. Now, what is the aim? The aim is to determine the transfer function that relates the height to flow. So here our aim is to determine the transfer function that relate the height, this H and Q0. That means in the variation in Q and this Q flow, accordingly the height is vary. So we find the relation between the height and flow. So for this we take conservation law. So according to conservation law, here we take only mass conservation law. So according to mass conservation law, we can write rate of mass flow in minus rate of mass flow out is equals to rate of accumulation of mass in tank. That means in other language we can say rate of accumulation of mass is equals to rate of flow in minus rate of flow out. So mathematically we can write this as here rate of flow in. So flow in is represented by Q, and rho is the density. So water flow and the water density is the rho. So we can write rate of flow in is equals to rho into Q of T. Same as we can write rate of flow out as rho Q0T, and rate of accumulation of mass in tank. So we can write rate of, here the mass is the represent in the terms of volume. So rho into V. V is represent the total volume in the tank, and the d by dt is the rate of change we can write. So here rho and rho is common or constant, so we can cancel out rho. And we also know V, volume, is also we can write in terms of area into H. So V is equals to A into H. So we get this equation as Q of T, here rho is cancelled, minus Q0T, and we write V is equals to A into H. So A is constant and dH by dt. So here H is the variation in the height of the tank. Now we know Q0 is equals to H by R. So putting the value of Q0 in this equation, we get Q minus H by R is equals to A dH by dt. We can write Q of T or Q, and Q0 is equals to H by R is equals to A dH by dt. Now we introduce deviation variable into the analysis. So at initial state, the process is operating at steady state, which means there is no change in the height of this tank. So initial state, there is no input and no output. So at that time there is no variation in the height. So we can write that this term dH by dt in this equation as 0, because at initial state there is no variation in height. So dH by dt is equals to 0. So by putting this value, and we can write the equation in steady state as Qs minus H of S by R is equals to 0. Here consider this equation is number is 4. And here in this equation Qs, this S, subscript S is represent the steady state value. So we write Qs and Hs. So see, this represent the steady state value of height and this represent the steady state value of input flow rate. And this dH by dt is 0. So we write dH by dt is equals to 0. Now subtracting this equation from this equation. So subtracting equation number 4, this is a 4 and by this 3. So we can write Q minus Qs minus H by R plus H of S upon R is equals to A dH by dt. Now we rearranging this equation, so we can write Q minus Qs is equals to, this term grow in the right hand side. So we can write minus H by R is equals to plus H by R. This plus is minus, so Hs by R, and this is a plus AdH by dt. Now we can also write this equation as Q minus Qs. Here 1 by R is common, so H minus Hs plus A d by dt H minus Hs. Here H is also we represent in the deviation form or in the steady state value, so we write H minus Hs. Now we define deviation variable as Q is equals to Q minus Qs. This is a Q is equals to Q minus. That means we represent capital Q is equals to Q minus Qs and capital H is equals to H minus Hs. So by putting this value in this equation, we get capital Q is equals to 1 by R into H plus A d by dt and H minus Hs is equals to capital H. Now taking the Laplace transform of this equation. Now we take Laplace transform of this equation. So we get Q of S is equals to 1 upon R. Here H is the H of S plus A. The derivation is S into H of S. So now we common in the right hand side we take H of S common. So we can write Q of S is equals to H of S into bracket 1 by R plus A into S. Now we rearranging this equation, so we can write H of S upon Q of S is equals to 1 upon R plus AS. So this is nothing but transfer function H of S upon Q of S is equals to R upon ARS plus 1. This R is multiplied by this, so we write this equation as. So this is nothing but the transfer function. And now we compare this equation, that means equation number 8 with the general equation of first order system, the first order transfer function. So we can write Kp is equals to AR, and we know tau p is equals to AR, and we know the tau p is the time constant. So we get tau p is equals to AR and Kp is equals to R, and R is the process gain. Okay. So in this lecture we study about what is first order system, and we take one example of first order system. Now in next lecture we will study about second order system. Okay.